Close to the surface.
So, welcome everyone to today's seminar. Our speaker today is Dr. Pierre Gentine from Columbia University, from the Department of Earth and Environmental Engineering. So I want to say a few words to introduce Pierre. He grew up in France and did his bachelor's degree at SoMAS, which is the French School for Aeronautic and Space Engineering, and he majored in applied mathematics. And after that, for 2 years, he worked on a hydrology project in Morocco, and then he came for graduate studies at MIT in the Department of Civil and Environmental Engineering, where he worked with Professor Dara Intakhawi. And his doctoral thesis was about the diurnal cycle of evaporation over vegetated surfaces. And since 2011, he is a faculty member at Columbia, and he has done really interesting work on how vegetation and climate are coupled, and how vegetation adapts non-linearly to climatic changes, and which is very insightful in understanding how land and surfaces and climate are coupled. So let us welcome Pierre Gentine.
Thank you. Thanks for the nice introduction. So today the talk will be mostly like land focused in terms of surface and energy budget. And so the title of the talk is Emergent Behaviors in Ecohydrology and Hydrometeorology. And the idea is to show that when we actually look at the coupled system instead of like standalone offline system, we actually see things that we wouldn't observe otherwise. And I would like to acknowledge my co-authors. So Benjamin Lintner is at Rutgers University, Paolo Dodorico at University of Virginia, Guido Salvucci at Boston University, and Gajan Sibandran at Ohio State. So the talk will be divided into 3 sections. The first one will talk a little bit about what is called the Budyko curve. So that's kind of a like well-known result in physical hydrology and surface hydrology, looking at the long-term water budget over like a watershed. And we'll see that there are kind of 2 reasons to explain this behavior: the fact that we have a very well-defined behavior across different catchments, across different climates, biomass types, and soil types. And we'll see that it's related to vegetation adaptation, but also to land-atmosphere interactions. Then we'll talk about something that has been known also like for more than 40 or 50 years in hydrometeorology, which is called the complementary relationship, and which tells us that the evapotranspiration and the potential evaporation, which is basically the atmospheric demand, the maximum rate of evaporation that we'll get from the atmosphere, are fundamentally coupled through land-atmosphere interactions. And we'll see that it's mostly done on a kind of on a large scale. It's a large-scale phenomenon, like synoptic scale. And then we'll talk about kind of an alternative to the common Penman-Monteith equation, which is used to estimate evapotranspiration. And we see that there is an alternative for that that kind of seems to work a little bit better, which is called the relative humidity variance. That's some new work that we've done. So first of all, what is an emergent behavior? The idea is to say that when you have complex systems, they can exhibit an emergent behavior where the temporal and spatial scale that you observe in the coupled system are actually very different from their constituent elements. 2 examples of that are what we call fish schooling here, where you have like individual fishes that actually are rowed together and have a very well-defined motion here that you wouldn't be able to guess if you were looking at one individual fish taken alone. And being together, they actually interact in a way that, in fact, sometimes it's more like more than just the constituent element, but it's the connectivity between all of them that actually creates the time scale and spatial scale. Same goes for the sand dune here, where we have this very well-defined pattern that is also due to like some interactions between the different elements, and that we wouldn't be able to guess looking just at individual elements here or individual entities. So meaning that here, if we look at the coupled system, sometimes the spatial and temporal scale that we'll get in the system might actually be different from what we observe from the like isolated entity. So the first thing is to just get back to what is called the Budyko curve. which relates the evapotranspiration to some sort of what we call an aridity index. So here I plotted here, so we investigated different watersheds over the continental US in a data set that is called the MOPEX data set. So it's a very well tested and calibrated data set available like freely over the web, where it's basically like 358 watersheds, very high resolution, and those are pretty small watersheds and pretty well defined. And they really span multiple climates, multiple biomass types, and multiple soil types. Here you can see a plot. This is the annual evapotranspiration, ET, so I keep on referring to ET for evapotranspiration here, divided by the annual mean precipitation for a given year. And here at the bottom, on the x-axis here, you have what we call the aridity index, which is the potential evaporation average again over a year, divided by the precipitation. The potential evaporation is the maximum rate of evapotranspiration defined by the atmosphere. So that's basically, if you will, the atmospheric demand in terms of evapotranspiration. So that's the annual value of potential evaporation divided by the annual value of precipitation, and we call that an aridity index, meaning that if you're below 1, you will be mostly water limited, and above that you will be you'll be energy limited here, and you'll be water limited when you're above 1. And that's what we would expect. We would expect that evapotranspiration will shift from these different limitation regimes and would go basically, in the limiting case, will basically reach the potential evaporation, which is the maximum value set up by the environment. So in this case here, what we have is that each point here is actually 1 year for a given watershed. Each color actually refers to a different watershed. So you can see that there is still substantial noise here around this curve. So I mean the fit, we don't have really just like a single line here and a single fit. Here, the black line that you see here was the original fit from Budyko, a Russian scientist, back in the 50s and 60s, and where he actually fitted a curve across different watersheds across the world, and he could get this estimate here based on a given aridity index. And we see here that we still have substantial spread if you look at the yearly average. But in fact, the original Budyko formula was actually defined on long-term averages or climatological values. And now if we look at long-term averages, so here we took 50 years data, so kind of climatological values, we see that we have here, so each point here represents one single watershed. We see that we have actually a better fit compared to the original Budyko formula. And here for the dashed line refers to a spread of -10 and 10%, which is typically the error bar that we have in the estimation of the components of the surface hydrologic cycle. What is kind of interesting here is that if you look at the different watersheds here, I put different patterns here. So the lozenges here refer to a case where the atmospheric demand or the radiation would be in phase with the precipitation. In this case, the square means that they are out of phase, meaning it's mostly like a Mediterranean climate where precipitation will be roughly at 6 months out of phase with the atmospheric demand. And then we have those small crosses that are pretty non-seasonal, like what we have here in the northeastern US, where precipitation is almost uniform throughout the year. So you can see that what is kind of interesting is that there doesn't seem, if we even zoom in here, so we zoomed in this section here, we see that there is really no like typical behavior for a given like in phase, out of phase, or non-seasonal behavior, which is kind of surprising, as we'll see in a second. Just keep this in mind that in fact the effect of phase between radiation and precipitation seems to be hidden in this picture, and we kind of just look at the long-term average. In fact, it seems to go out with modeling studies. So back in the early 90s, Chris Mealy at GLDL looked at the Budyko curve from a theoretical perspective using a bucket model. And he forced the model with different like seasonal cycle of precipitation and with intermittent precipitation using a Poisson process. And in fact, in those two pictures, what you can see is that he drew basically the results from the theoretical model, exactly the same as the Budyko curve. And what he did is they studied the effect of the phase. So here, this delta here refers to the phase of the atmospheric demand, potential evaporation, and the delta P refers to the phase of precipitation. And what you can see is that here, in this picture, precipitation and evaporation are out of phase. And here, they are in phase. The W here refers to the mean soil moisture value that we have in the different watersheds, but let's forget about that for this. The main picture that we observe here is that when precipitation and the atmospheric demand of evaporation are in phase, we'll see that we will have actually an increase of the evapotranspiration. So basically we move up here in this kind of Budyko phase space. Okay? So instead of staying in this area, we'll actually move up here, meaning that we will basically get more evapotranspiration, more yearly evapotranspiration. Okay? And in this model, we should keep in mind that this was done assuming that you had the constant rooting depths for the vegetation across the different watersheds. Now, if we go back to like a very simple soil moisture budget, so this is a soil moisture budget at a point or over some given area, and refers to the porosity of the soil. ZR is the rooting volume per unit area, so sometimes called the rooting depth, but rooting volume is actually more accurate. This is the soil moisture, the rate of change of soil moisture. This will change as a function of the input of moisture, which is basically the precipitation minus some possible canopy interception, which we'll call Ri. Here, some leakage term. This leakage term is actually the infiltration excess, so basically what is not able to infiltrate into the soil and has to run off. The saturation excess when the bucket will be basically filled up and will actually have to run off. And then the infiltration to the deeper layer onto the groundwater. And this water will not be accessible anymore, except if we have some deep roots stepping into the groundwater. But typically it won't be available anymore, and so will be lost. And this term is the evapotranspiration, which actually depends also on soil moisture. The evapotranspiration is divided into a bare soil component here and into a vegetation component here. So here vegetation refers to the vegetation fraction. FC is some sort of canopy efficiency for potential evaporation. So it's roughly an indicator of the aerodynamic resistance and of the stomatal resistance, and basically how easy it is for the vegetation to actually pull up the water and transpire. Here, EP is the potential evaporation, so basically the atmospheric demand from the atmosphere. This term is a vegetation stress term, which depends on the wilting point of the vegetation and some other factors. And here, this is the bare soil component, so we don't have this efficiency coefficient of the stomatal resistance. And so, if we look just at this equation, it makes sense that if the precipitation and evapotranspiration the precipitation and atmospheric demand, potential evaporation are in phase, of course the evapotranspiration of our year should be at maximum. In fact, in that way, we'll minimize the infiltration. So each time we'll have water, basically we'll right away try to evapotranspire the water. So we basically minimize the losses through runoff or infiltration deeper in the soil. So ideally, based on that, this would be like the optimal way to actually use the water, to have in-phase potential evaporation and precipitation. And what we would expect is that we should see, if we go back to the observation, we would expect that when they are in phase, when precipitation and potential evaporation are in phase, we would expect to have actually higher evapotranspiration, so to be in the higher section here of this curve, which is actually not what we observe here. So there must be something kind of hidden there. So in a sense, what is hidden is that this rooting depth here and this coefficient, the efficiency can actually adapt to the local climate. In fact, it's just saying that, in fact, the vegetation is basically adaptating and creating its habitat here, which depends on the climate the soil, and therefore the vegetation has to adapt. So in the most general way, what Budyko says is just this, that we have a relationship between the climate, soil, and vegetation. That's really the minimum we can say or infer from this curve. And so it means that they are really independent or interdependent. So what we did is that the soil type, we can get a pretty good clue of what it is based on those observations, because we have pretty intense USDA observations. For the vegetation fraction, the veg term that we had before, we can use some remote sensing products, so it can give us a pretty good idea of what it is. And we can get also a pretty good sense of what the aridity index is over on annual time scales, and what is the phase tau between the potential evaporation, and the precipitation. So based on that, those terms will be kind of given for us, and all the rest that we don't know in the model will be the canopy efficiency to transpire, the routing depth here, ZR, and the rainfall interception. So those are the only three parameters that we need to know, and to some extent they need to fit the Budyko curve, because we saw that there was actually little variability in the observations for a given climate and so on. So based on that, we just say that, okay, we assume that the Budyko curve is actually the truth, and we just invert this curve so that we get basically the best fit to the Budyko curve. And then we obtain like a triplet of optimal canopy efficiency, routing depths, and rainfall interception across the different watersheds. And we could plot those different triplets as a function of, say, the mean aridity index, but also as a function of the phase between precipitation and potential evaporation. So now if we look just at the effect of the mean aridity index, so we don't see it well here, but that's again the mean potential evaporation divided by mean precipitation. And if we look at the canopy efficiency, we can see that there is a small drop, but there is still lots of variability. So roughly, I mean, there is little change when we go to a more arid basin or more arid climates. What is more interesting is now if we look at the vegetation routing depth, we see that there is a maximum here in the middle where we're roughly at about 1, a little bit less than 1, where basically the atmospheric demand in terms of evapotranspiration is roughly of the same order of magnitude as the precipitation. And then we have a drop again here, and the routing depth also goes down again, which is coherent with like several observational studies where actually the deeper routing system are observed in like this intermediate range of aridity index. And so that's very typical. What it would say is that basically when you have lots of water, so when you are in an energy limited regime, you actually don't need to invest your carbon in the routing structure, because the water is available and you will get basically everything you need. So, I mean, a shallow water routing system actually is sufficient for you. Now, if you go to like more arid systems, so a little bit drier, then it makes sense to actually invest your carbon in a deeper routing system, because you want to actually cope with water stresses and punctual water stresses that you didn't have before. So this would be a way to actually create resilience in the system to actually deal with like some drought events. Now, at some point, if you become really, really dry, I mean, there is almost no interest in actually building up a deep routing system, because it's too risky for you. If you have the carbon, if you tend to invest into the routing system, it can take time, and it might not be the most viable solution for you. You maybe better have some other strategies to actually keep the water. So, which also makes sense to actually reduce the investment that you make into your internal carbon. One way for that would be, for instance, like looking at succulent plants. You don't invest too much into your rooting system, but you actually try to keep the water inside you through like some capacitance term. Now, what is more interesting is even to look at the effect of the phase and the seasonal cycle. So again, if we look at the evaporation efficiency, we see that there is almost no change based on the effect of the phase difference between precipitation and potential evaporation, which is here given in months. So that's basically the peak. We are looking at the peak between precipitation and the peak between potential evaporation. So again, very little difference. The main difference is again observed over the routing depths, where here we see that we get the maximum when we are at about like 6 months difference between precipitation and potential evaporation, meaning which is typical of like Mediterranean climates, where in fact you don't receive the precipitation when you have the atmospheric demand. So what you're trying to do is actually to invest into a deeper routing system so that you can actually use the water because you kind of stored it in the soil, and then you'll use it later when the radiation or the photosynthesis will be major later in the day. So that way you will maximize your carbon creation and your carbon and the biomass creation. So that would be the best and most optimal way to actually do that. So we see that also kind of nice in the data. And of course we ran some significant tests on that, and it works. Okay, so now, so what is kind of hidden also in this Budyko curve is we saw that vegetation seems to be a big player in the stability in the Budyko curve, especially on the seasonal time scale. Now, what is kind of interesting is that in fact the evapotranspiration that we emit from the surface is actually coupled to the potential evaporation. I mean, because when we get more moisture in the atmosphere, what we'll do is we'll reduce the gradient of humidity at the surface, and therefore we will feed back into the evapotranspiration, and we will tend to actually reduce the evapotranspiration later through a boundary layer or large-scale moisture feedback. So this has been known for a while here. So this is called the complementary relationship, which is originally done by Bush and Morton in the 60s. And what they noticed is that if you actually measure evapotranspiration and potential evaporation over like several time scales, going from like daily to weekly to monthly, you can see that in fact they go hand in hand, and they go in the opposite phase. So if you increase potential evaporation, you will actually see just like the this is evapotranspiration, it will just go in the inverse direction as potential evaporation. So people have hypothesized different behaviors, saying that in fact maybe there is kind of an optimal mean value here, so that you always need to basically partition the energy that you have, the latent energy that you have, into either evapotranspiration or potential evaporation. So there have been lots of like kind of wavy theories to explain that, but it was not still clear. So the idea is to say that now if we have like evapotranspiration here, if we increase, for instance, some moisture, what can happen is that you will increase evapotranspiration. But if you increase evapotranspiration, you will actually decrease the atmospheric demand because you're moistening the atmosphere. So it will have a kind of a negative feedback here on some moisture and evapotranspiration. If you increase evapotranspiration, you could also get more or less precipitation because you will influence the moisture in the boundary layer, and this could actually feed back into the sun moisture loop. Another effect is that if you change the evapotranspiration, you will also change the energy partitioning at the surface, and you could actually generate pressure gradients, which would lead to moisture convergence, for instance. So if, for instance, you were to reduce the evapotranspiration, you can induce moisture convergence. So you would have two ways to actually generate precipitation, through indirect moisture convergence, or like to local, more like recycling effect through like boundary layer recycling. So what we did is we looked at kind of an idealized large-scale model of land-atmosphere coupling. So in its original formulation, the model was developed by Ben Lindner and David Nealon, where they were looking at a transect here going from the Atlantic Ocean to the tropical South America. Here, basically, here you would have the Amazon, the Nordeste region, and here you would have the Atlantic Ocean. And this system is forced basically by a given advection term here. And we let the system evolve as a function of the direction here as we move along in the direction of the land. So this would be the x direction, if you will. And what we observe is that we get very little convection here on the sides, and it's roughly very dry most of the time. And here, all of a sudden, we have what we call the convective margin here, very sharp transitional region between dry and wet, where here you have lots of convection and pretty active convection. It's a strongly convergent region of moisture. So what we did is we looked at the vertically average heat and moisture budget here, so average over the entire atmospheric column. So if you look at the rate of change of the temperature, it will be balanced basically by the temperature convergence, by the precipitation here, heating, by the net radiation, which is basically the radiation difference between surface radiation and emitted radiation at the top of the atmosphere, the sensible heat flux that we have at the surface, and this is here the advection term. Same goes for the specific humidity here integrated over the column. Same here, we have a divergence term here, moisture convergence. Here we have a precipitation sink. When we have precipitation, we have a sink of water in the system. A source term, which is the evaporation at the surface here, and again this advection term. And here we assume that the advection is just given at the sides here on the edge of the system. So we just impose the advection here, and the whole system evolves through the land-atmosphere coupled system. So what we got is that if you look at the sensitivity of precipitation to a change in soil moisture, so that's delta P to delta W, so what is the effect of soil moisture on precipitation? In fact, precipitation can be defined can be decomposed into like 3 different sources. The moisture convergence here, which is the red line here, the moisture advection, the horizontal advection that we have here, green line, and the local evapotranspiration, which is the blue line. So if we look at the sensitivity of precipitation to soil moisture, what we observe is that we basically have a U shape, which was a little bit surprising at first. So we get this sensitivity that increases on the dry end and increases again on the wet end. And in the middle, we have kind of a minimum value for that. Now, if we look, in fact, the reason for this sensitivity change is actually very different. If we look at on the dry end, so on this side, most of the precipitation is actually just induced by evapotranspiration. So it's mostly like a local recycling effect. We basically precipitate the moisture that we have locally, that we provided locally. Now, as we move along into this more like moisture or energy limited regime where we have more moisture, it becomes more like a 2D or 3D effect, where in fact the contribution of evapotranspiration becomes very small here and almost zero when we are really very wet. And in fact, most of the contribution is given by the convergence of moisture, which is typical of what we would guess of like tropical regions where the precipitation roughly balances the moisture convergence on like longer time scales. And here we also have the effect, some effect of the advection. But what it means is that we already have like 2 different regimes where here it's mostly like a kind of a 1D picture where evapotranspiration will be recycled into precipitation, and then it's here on the wet side it's more like a 2D picture where we need the evaporation contribution becomes very small, but it's mostly the induced convergence and advection that will actually generate the precipitation. Now we looked at what is the effect if we kind of shut off the dependence of evapotranspiration on soil moisture, which is a pretty strong dependence. So in a sense, we're kind of shutting off the surface hydrology. And so we have 3 different cases, or 2 different cases. Here is the baseline, so what we had before, this U shape that we observed. Here, when we shut off the evapotranspiration coupling with the soil moisture, we see that we have basically no sensitivity change on the dry end. And here we see again the effect of convergence. But at the beginning here, we had almost no sensitivity. And this here shows the difference between the two different processes, meaning that here we can see basically the effect of the land-atmosphere coupling on the precipitation and the change in precipitation regime as we move along here along the soil moisture gradient. And here we can see that we had kind of a positive feedback here, and here we had a negative feedback. This positive feedback was induced by the direct evaporation of evaporation, which makes sense. More evaporation leads to more precipitation, therefore we have this positive feedback loop. And then here is like a negative feedback loop through the moisture convergence. So kind of, yeah.
What would be a spatial scaling of those different regimes? I mean, how would they relate to the boundary that you showed earlier in terms
So-
of their relative importance spatially?
So this is on a very large, so it's like hundreds of kilometers here that we're dealing with. It's not like local processes. We're not dealing
But I
directly
mean
with.
along the ocean coastal boundary, you're talking.
Oh yeah, like thousands of kilometers here.
Would be,
So these boundaries is like several, like thousands of kilometers.
so that's 1,000 kilometers.
Yeah.
Right. So your minimum, your transitional region is hundreds of kilometers.
Yeah, right.
inland.
Yeah.
Right.
Yeah.
So like Northwest is like several degrees latitude.
Yes, right, exactly.
So where I think this was done.
Yeah. So yeah, that would be basically the northeastern region, yeah, and the Amazon. Okay, so in fact, based on this model and the kind of the implied large-scale and atmosphere coupling, we looked at and we diagnosed the Budyko curve. So again, the same plot as what we had before, and we plotted the evapotranspiration here divided by precipitation, again as a function of potential evaporation divided by precipitation. The only thing that we change is in the surface hydrological model, you always have a dependence on soil moisture. So we tested different dependence on soil moisture. So S is the soil moisture. We try different factors here. So like to the power 2, linear, or to the power 4. We try different things. And in fact, what we observe is that typically the Budyko curve is between like S to the power 2 and S to the soil moisture to the power 2 and soil moisture to the power 4. But the thing is that the overall shape is pretty well characterized by this simple model. So we are actually able to actually characterize that from a large-scale land atmosphere perspective. Now, if we look and go back to the complementary relationship that we had before, again, now we see that the evapotranspiration and the potential evaporation will be coupled through this large-scale coupling. So here we had, so this is from a work by Petition and Salvucci in 2009, where they looked, so each circle here represents like amounts of data here that they had over the Kansas Prairie. And here, this was a fit of the data that they had. So this is the potential evaporation, and here the evapotranspiration. Same here for a different watershed, the Little Washita watershed. So they got kind of similar results. In fact, we got, with the same type of model, we got exactly the same type of behavior. In fact, we even looked at the slopes, and they look exactly like what they had for the fit of their data. So here will be, again, this complementary relationship as a function of soil moisture. So here is evapotranspiration, and here is potential evaporation, and they go kind of hand in hand in a complementary way. And in fact, it's not like they are not exactly the inverse of each other, but there is kind of a coefficient, like evapotranspiration would be potential evaporation to minus B. And in fact, this coefficient is really very much the same as what we actually observed on the field. So it gives us like a good validation of the model, like using observations. I don't have the data here. We have not studied the data yet, but the fit is actually very good. So again, this kind of large-scale and atmosphere coupling also explains this kind of complementary relationship. In fact, if you look at this complementary relationship, it typically fails when you have really intense advection and really like a front, for instance, passing over the system. So that's typically when it stops, where kind of the equilibrium that you had in your system basically collapsed and was failing. So just in conclusion for the Budyko curve, it seems that the long-term stability of the Budyko curve is induced by large-scale and atmosphere coupling between precipitation, potential evaporation, and evapotranspiration, and also to vegetation adaptation, and most importantly by rooting depths adaptating to the system, and especially imposing or playing basically the game with the seasonal cycle, so that we could put in kind of in phase the availability of energy and the availability of water, so that in a sense you're storing water so that you can use it when you actually have the photosynthesis available. Now, let's just look at kind of a different problem. This is the Penman-Monteith equation. So that's the typical equation that people use to estimate evapotranspiration over land. So it's based on the surface energy budget, and also based on the typical resistance-like formulation of evapotranspiration. So the idea is we can basically estimate the evapotranspiration based on here the net radiation, which is basically the net radiation between short wave and long wave radiation, between what is incoming at the surface and emitted at the surface, minus what is going into the ground heat flux. And so here, this is the slope of Clausius-Clapeyron, the saturation vapor pressure. So this is the density of the air, specific heat of the air. This is the aerodynamic resistance. So basically, what controls the transfer of heat and moisture from the surface into the atmosphere. So this is basically representing the turbulence and the efficiency of the turbulence for the transport. This is, again, the saturation vapor, water vapor pressure, which is a function of the air temperature. And this is so this is the water vapor pressure measured on the side. So in fact, the air temperature and the vapor pressure, you can measure it using a weather station, typically. The net radiation, you can measure it if you have like some observations of the short wave and long wave radiation. So you can do that in different ways, but you can have local observations or you can use remote sensing. The issue is this ground heat flux term. Typically, we cannot estimate it because it would mean that we need to bury some sort of solid flux plate into the soil, and you cannot do that if you want to look at large scale values. Here at the bottom, we have the psychrometric constants. Here, this is RS is the stomata conductance, so how the stomata will actually modify the evapotranspiration, and here RA is the aerodynamic resistance. So in this model, the main unknown is actually this stomata resistance. So all of the work that have been done mostly in the land surface community using, for instance, remote sensing is trying to estimate this term. And this stomatal conductance term is really the transpiration efficiency and depends on lots of factors. So people have tried different things like using time series of infrared temperature to actually estimate this term, but I mean, it's always very highly empirical. Oh, okay. So one way around this was introduced by Priestley and Taylor. The main issue is actually getting this stomata resistance term. So what they said is because of land-atmosphere coupling, maybe, in fact, we don't need this stomata resistance term, because if we provide more moisture into the boundary layer, we would have higher specific humidity, lower temperature. So in a sense, what we observe on the field with the weather station should be sufficient so that we could actually estimate evapotranspiration. And we wouldn't need the stomata resistance. So what they said is that instead of having this term, the stomata resistance, they said that it will be roughly this term here that we have at the numerator times some coefficient alpha, which is kind of a correction factor, which should depend on land-atmosphere coupling. And that way we wouldn't need the stomata resistance. Okay. Of course, it's highly empirical based on like very few case studies, but lots of people have been using that. But in reality, it doesn't really work well, of course, because there is lots. I mean, a good example is if we have a heterogeneous landscape, if you have actually measured with a weather station, say over an irrigated field and a neighboring like very dry field, if you look at the actual air temperature and specific humidity, you don't see much of a difference between the two regimes, just because of the advection and maybe breeze effect that you will generate. But the evapotranspiration will be way different between the irrigated field and the neighboring field. So in fact, you would expect that there should be like substantial deviation from that. So what we've done is we've been looking at lots of data, like weather stations data and flux measurements data. So you have those flux measurements data, so it's a network called FluxNet, which is located throughout the globe. So you have it in the US, everywhere. And they basically measure the fluxes of like momentum, like turbulent fluxes of momentum, heat, moisture, and also carbon at the surface. And they also have like neighboring weather stations, measurements of radiation nearby. And what we've shown and we've looked at looking at the data is that if you look at the data and you were to look actually at the atmospheric profile of relative humidity, it seems that to some extent the relative humidity is always trying to conserve itself. So it's trying to actually minimize, if you look at the daily shape of relative humidity and its variance, or the variance of the profile near the surface in the first 20 meters, it always tends to try to minimize itself. So if you now have, say, again, Penman-Monteith or whatever model you have with a given stomata resistance, if you plot that as a function of the stomatal conductance, you will see that you have actually a minimum here. And in fact, if you look at the observation, this minimum is exactly where you actually have your observation of evapotranspiration. So, which is kind of an interesting emergent behavior of the system, meaning that we just need to actually scan different values of stomatal conductance, and this should be able to actually give us the evapotranspiration. Okay, so we tried that over different regions. One was over the humid Northeast, so this is measurements taken at the Duke forest, again, like very tall forest, very humid. And the blue line here is the precipitator results. The measured data from the flux, like tower observations measuring the turbulence of evapotranspiration, is actually the green or yellow line, sorry, I don't know. And the estimated value that we got from this minimum variance idea is the red line here. And this is, we estimated evapotranspiration every day for like, here it's plotted as a function of, just for a single year, as a function of the Julian day. And this is latent heat here in watt per meter square. What you can see is that there is substantial difference between the precipitator result, which always overestimate the actual evapotranspiration, and the observations here in green. Now, if we look at the minimum variance strategy, in fact, we have a very good fit with the observations. Okay, just based on this very simple argument that, in a sense, the stomatal conductance has to kind of evolve in a way that, or the stomata has to open in a way that actually minimizes the variance of relative humidity, which is kind of interesting because relative humidity is not a conserved variable in the system. What is conserved is actually the specific humidity and the potential temperature. But relative humidity is not conserved. So, I mean, it's kind of interesting that it's still trying to evolve in a way that is trying to constrain it. And in fact, I've studied that in some other contexts where they actually see that relative humidity in like lots of different contexts is actually trying to remain very stable, which is kind of interesting because it's highly nonlinear. Now, if we look at a very different climate, this is a Mediterranean climate. Again, we tested this minimum variance idea. Here, again, we have the precipitator data, precipitator results, and green line here is the observation from one tower, and there was a second tower here in the red line. And again, here, this is the results that we had. So again, a very good fit with the data, and we get this very nice seasonal cycle that the precipitator results didn't get in this particular Mediterranean climate. For precipitator, basically what they picked up is just the seasonality of radiation and precipitation. Now we also looked at an arid case in the southwest US, in Arizona. Same stories, precipitator always overestimate a lot evapotranspiration because in this case the vapor pressure deficit or the aridity from the atmosphere is always very high, so you expect to actually get, most of the time always get lots of evapotranspiration just because of this vapor pressure deficit. And so you very strongly overestimate the actual evapotranspiration. So again, the green line is the measured value. Estimated is what we get from this minimum variance argument of relative humidity. And the final one in the northern Great Plains. This is an irrigated field, just to show that it works also like irrigated. And again, compared to precipitator, it works very nicely. We get a very nice seasonal cycle, and we also get like the diversity that we observe in the data. So again, for a very different regime. And sorry, this one was rain-fed, sorry. So again, we got this kind of nice behavior. So in the end, so this minimum variance argument for the relative humidity seems to work really well. We're still puzzled that why is it actually working. And so we've tried several things, and it seems to be related to like boundary layer feedbacks, but also like to long-term behavior. And we've done some radiative convective equilibrium tests. And it seems to be related to the fact that the atmosphere tends to get to an equilibrium much faster than the soil. So in a sense, what you would observe in the atmosphere would be a good reflection of the kind of equilibrium state between the evapotranspiration and precipitation. So it means that it's kind of related to what we observe in the atmosphere, and this kind of relative humidity that we observe, and this minimum relative humidity variance seems to be related to a kind of an equilibrium in the atmosphere. And now the next step is to actually map daily evapotranspiration over the US and to further test this model across the globe to make sure that it works in different climates. But so far, I mean, the results were pretty good. So just in conclusion, so if we look just at the surface hydrologic cycle and mostly at the evapotranspiration flux, we see that there are several type of emergent behaviors. One of which is actually the Budyko curve that is due to like feedbacks between the land, the vegetation, and the coupling with the atmosphere. We also saw that there is another one which is called the complementary relationship that also sets up a very nice relationship between evapotranspiration and the atmospheric demand, the potential evaporation. We also saw that to some extent the lower, the surface layer in the lower atmosphere tends to work at some sort of state of minimum relative humidity variance. So it tries to minimize the variance that it has during the course of the day for a reason that we are still trying to understand. And these emergent behaviors are really due to the coupling between the ecology, the physiology of the plant, the somatal behavior, the adaptation of the biomass, but also the coupling with the atmosphere. And not surprisingly, the surface heat fluxes are really the boundary condition for all of those systems. For the ecology, as you know, like the flux of carbon and evapotranspiration and heat, but also for the atmosphere. So we would expect to have such feedbacks. And so just the main point is that if we really want to understand better, predict the evapotranspiration fluxes across different time scales, we really need to look at integrated and coupled systems. That's kind of the only way to go, I believe. So with that, I end up here. Thank you.
Any questions for Pierre?
Yeah.
Yes. I did not see any surface wind included in the equations. Because I mean, the surface wind is not explicitly included.
Yeah, in fact, it's hidden here in the aerodynamic resistance. So, yeah, here it's basically mostly depending on wind.
So, Bob, you had a question?
I had a question about your soil moisture model that you showed, and you talked about root volume. You also talked about root depth.
Yeah.
And I'm wondering what kind of an integration scale do you need to apply that model? And obviously, if you go out and try to measure such a thing, it's highly variable.
Yeah.
And both seasonally and spatially. And I'm wondering how that parameter, is that teased out of your overall fit?
Yeah.
Or is it actually measured?
Yeah, so, I mean, we didn't try to actually compare it because it's kind of an effective parameter. So I wouldn't really go on the field and exactly try to measure it because it's, as you say, it's highly variable and you have different species and maybe you will have bare soil here and no roots actually. But it's kind of just an effective, bulk rooting depth or like rooting volume. How much volume of roots I have per unit area. If I look at this large scale, that's roughly what it is. In fact, this is just kind of a simplified version of a typical land surface model that could be used in a climate model, but just highly simplified.
So in the original data that Budyko used to come up with this diagram, so like what scales was it for, like?
It's a watershed. It's shiny at a watershed.
Like with different time, different distance scales, or were they all very large?
No, mostly like small and medium sized.
So I think that doesn't like so.
Yeah.
Why shouldn't it apply to smaller catchments?
So like larger catchments, you run into troubles. I mean, for instance, if you look at a very large catchment, say the Mississippi, then of course you also have like a climatic gradient, precipitation gradient, lots of things that can.
So I think Professor Allen would be more interested in smaller regions.
Okay.
So should it apply to smaller?
As long as it's a watershed, I would say it's fine. But if you look at those models, I mean, the issue is when you want to actually apply them at a point scale. I mean, the assumptions are kind of, I mean, even in the most sophisticated land surface model, they always assume that you have basically a uniform horizontal layer of roots that can tap everywhere. And they have like some vegetation fraction, which is actually just the emerged above soil canopy layer. So it's kind of funny because you have they assume that the rooting depths actually extend all the way through the square that you have or the box that you have, but for the vegetation or above canopy, it's just one part of it. And they don't really consider like the root to shoot ratio, or the fact that you have actually a disconnect between like several roots, and like some parts have no roots, so maybe you would expect more or less water depending on the case here. So I mean, I think it's still a challenge, and that's like a big issue. And trying to have a good representation of this heterogeneity is a challenge actually, because it's a very 3D effect, right?
I'm not very familiar with the Budyko theory, but did he actually derive that formula, or it says like feet, or just guess? How he came up with it?
For the curve? No, he used several points, like lots of watershed data across the.
Yeah, but it just lucky guess. It's not really derived in some.
It's like semi-empirical. So he had like he basically looked at the asymptotic values, and he fitted the line in between. So that was kind of the best fit in between.
So that curve have. I think those extreme values are not very interesting, right?
No, yeah, you're right.
So most interesting is this where you have maximum curvature.
Yeah.
Have you looked how it's going to change in warmer climate? Is it going to?
No, I have not looked at it. Yeah. I mean, there were a few papers on that, like trying to diagnose the Budyko curve in climate models, and I mean they tend to do a poor job compared to observation, because in a sense, especially, this was a little bit earlier, but the vegetation tended to be a little bit too static to actually accommodate for what was going on in terms of precipitation, flux, and atmospheric demand. So that was a major issue. I mean, the spread was tremendous.
But this curve can be used for models of adaptating vegetation.
Yeah, right.
That's why.
Yeah. No, in fact, I was thinking about that, like trying to impose that, so that we have like a way to constrain the billion parameters that we have in those models.
So yes, please.
Could you please go to the page where you give a couple of equations for the, I think for the energy budget and for the moisture budget?
Yeah. This one, right?
Yeah. I have a question. Are these quantities like temperature and the moisture dimensionless variables?
Yeah, sorry. I forgot to say they are dimensionless. Yeah, sorry. Otherwise, you wouldn't have precip the same way here and there. Yeah, here, yeah. I forgot to say it's dimensionless. Yeah, in fact, it's not actual temperature. Yeah, thank you. Sorry.
We have no more questions, so let us thank our speaker.
Thank you.